Let's start it. Hello, everyone. My name is Wang Xidong, and the second-year PhD of Professor Wang Benyou. Today, I'm honored to give you guys a presentation about our recent studies on multilingual and medical LLM. I'm feeling a bit under the weather today, so my throat is a little bit hoarse. Please bear me. Today's presentation will be divided into 4 parts. First, I will briefly introduce the background to emphasize importance and fill in the context for this presentation. And then I will briefly introduce the and then I will show the primary scaling to 12 languages to help get the first-hand feeling about the task. Then I will introduce our exploration of multilingual mechanism, covering the new analysis tool, new phenomena, and new MOE variants inspired by this. Finally, I will show how we efficiently scale the method to more languages and larger models and the main results and the application study for it. So let's begin with filling in the context of today's topic. Sorry. Before the presentation, let me briefly introduce myself. I'm a second-year training guy. I mainly focus on medical LLMs and LLMs interactivity. And I trained a lot of models that get popular and gain some impact within the community, both in code wrap, store, and citations. So why multilingual medical is so important? First, communication with patients in a language that is consistent with local culture can lead to a smoother conversation with patients, and patients are more likely to experience better services and listen to advice. In addition, if we consider some extremist cases such as death notifications, cancer notifications, and depression treatment, using local languages, using local languages can comfort patients. With and the meaning of the expression can be more profound. Since multilingual health is so important, what can the existing LLMs do? Let's take a look with an example. This is an example of a complex patient described in Chinese. When I translated the question into English and asked the ChatGPT, we saw the answer was clear and detailed. But when I translated the question into Hindi, I saw that the answer was very rough and the words did not express meaning and did not serve the questions. In theory, we see that the LLM knows how to answer the questions and also knows how to translate between Hindi and English. That to say, the knowledge is complete in this case. But even so, the ChatGPT's answer in multiple languages is still not satisfactory. Not to mention that it's necessary to combine local living habits, cultural customs, and accessible drugs for local adaptive diagnosis and treatment. So after understanding the relevant background and motivation, let's use the data and the experimental results to get the first-hand sense of the development of the field. As we all know, data is the foundation and premise of all delicious ideas. A dirty, unclean data set can make a wonderful idea dim. So only data that matters may make sense at the start of a project. The logic of collecting data in our paper is to completely replicate the information and the sources of doctors during their growth. Through communication with doctors and medical students, we summarize 10 their information sources as shown in the picture. And use this as a category and entry point for calculating data. We carried out heavy data collecting and cleaning work. Finally, the statistic distribution of data by language is shown in the red part of the figure. It can be seen that even among the 12 languages, the distribution of data volumes is extremely reduced, which also reminds us that in order to adapt to more minor languages, the difficulty of data collection has increased sharply. Then we use the collect data to train a small model to verify the data quality and performance improvement. The second row of the table shows the results of our evaluation after training with the data of each language specifically. It can be seen that the performance has improved, which further verify our data quality. The third role is to train with data from all languages. It shows that compared with individual training, the performance of joint training continues to improve, which verifies effectiveness of multilingual training and further motivates our article methods. And the third role is to explore the impact of code and mathematical data on model performance. The model performance will decline without using this part of data, highlighting the necessity of it. We also tested some closed source and open source models. The results show that there is still a lot of room for improvement in the performance of open source data and of open source models. So getting here basically means that we have built a solid and low limit stage for our innovation of methods. And at the same time, we have gained some first-hand experience, such as the performance of existing open source models is not as good as boasted, and the difficulty of collecting data in other minor languages. So on this basis, considering the previous case, since we have relatively complete medical knowledge of minor languages saved in major language, can we achieve our goal to more than 50 languages by using generalization between languages? If this can be done, and there is no need for collecting a lot of minor languages data. Starting from this point, we conduct research on multilingual generalization. Because we want to study the generalization and the interpretability of language, we need to know which part of the model parameters are related to which language. Only in this way can we easily study the relationship between different languages, and we use the word modularity to describe the relationship. And the MOE architecture is very compatible with the modularity. Here is a brief explanation of what MOE is. As described in the picture, we all know that a transform block can be abstract as the architecture on the left, which consists of attention block, MMP block, and norm models. Where a transform block has only one MMP, the model of MOE architecture has many MMP and a routing weight. Actually, a small MMP is used to select several MMPs with larger weights based on the token input. But in this way, we don't know which part of the model parameters are related to which language, so we do a little modification here. Specifically, as shown in the middle figure, for the training data of a specific language such as French, in addition to MMP activation with high weight, we let it specific to route to a certain MMP. In this way, from the perspective of the training of the MMP, which is Expert 2012, it had trained all the data about the language. And a natural question will be that why do we still keep the MMP activation with the highest weight? Why not just activate the specific MMP? We thought so at first, but unfortunately, it doesn't end well. As you can see in the table, the former described method when we shown it as language-specific routing. The model performance is seriously impaired under this method. One possible explanation is that the reason why MOE work is because its robustness or so-called functionality. That's to say, from the perspective of knowledge storage, the same knowledge storage stored in different MLPs and all X are not put in one basket. From the perspective of MLP training, MLP not only learns the knowledge when asked it to learn, but also learns the knowledge of other experts to improve its own performance. So in the end, we can see in the table, after small changes, our method, which we call hybrid routing, balance performance while maintaining interpretability, and even show good generalization with high score for untrained minor languages. At this point, we have prepared the tools to study multilingual mechanism without compromising model performance, and the formal exploration begins now. Specifically, we conducted a static analysis of MOE routing strategy and counted the distribution of model rating on data of 5,000 tokens sampled from 12 languages. As shown in the figure on the right, the x-axis of the picture presents different language experts, and the y-axis presents the number of model layers. The figure on the left is an abstract summary of the routine paradigm about the rat. We can see from the routine analysis that except for the last two layers, the routine experts in the remaining layers are relatively concentrated, and only the last two layers are decentralized. This implies us that only the last two layers need MOE modularization, where the previous layers actually only need to be dense. To verify this hypothesis, we conduct the following experiment. We MOE the last 1, 2, 3, 4 layers respectively and compare their performance. We found that in terms of performance and generalization, the model reached the peak when only the last two layers were MOE and even exceed the MOE with all layers. So we get an architecture which we called post-MOE and the training method which we called hybrid rating, that is both efficient, generalizable, and interpretable. So at this point, we are about to achieve our goals, which democratize medical LLMs for 15 languages efficiently. In former slides, we obtained the architecture, post-MOE and the training method, hybrid method. Although it's very efficient, we also found that if we want to directly use this method for 15 languages, we need 15 experts, which is obviously a huge cost. A very intuitive idea is to merge experts. So how to merge? We merge the language families according to the language pairs, which is the language family. We merge the language with respect to that language family which they belong to. As shown in table, we obtain a post-MOE model which only requires 7 experts. Finally, we compared our method with existing models, and the results were much better than the open source model and close to the closed source model. At the same time, we also verified the effectiveness of our method on various model scales and convinced its scalability, which verifies that our method is a beneficial contribution to the community. So that's all for today's sharing. We'll first briefly introduce background, and then we will show the primary scaling to 12 languages start with data. Using data and MOE architecture, we explore the multilingual mechanism, covering the new analysis tools, new phenomena, and the new MOE variants inspired by this. Finally, we efficiently scale the method to more languages and larger models. So that's all for today's sharing. Any questions?